Hi everyone, welcome back to Lulumath. This video is on challenging factoring completely problems. So the background knowledge that you will need is you'll need to know how to factor completely, because this video is taking it up a notch and we're going to do some more challenging examples of factoring completely questions. So if you need a refresher or you need some help with that, please make sure to check out the video at lulumath.com or on the Lulumath YouTube channel. This video is part one of two challenging factoring completely videos. So if you want some more examples besides the ones that are provided in this video, make sure you check out part two. So let's get right into it. Our first example is asking us to factor 36b to the power of 6 x to the power of 8 minus 36b to the power of 6. Now, don't forget there's a list of questions that you're going to always want to ask yourself whenever you are factoring completely. Our first question is there a GCF? So looking at both of my terms here, I can see that they have a 36 in common and they have b's in common. So the answer to this question is yes, there is a GCF. So I will factor out 36 from both of my terms since it's in common. And I also will factor out a b to the power of 6 because that's also in common. So when I do that, 36 divided by 36 is 1, b to the power of 6 divided by b to the power of 6 is 1, and then I've got 1 times x to the power of 8 left over, or just simply x to the power of 8. Now, negative 36 divided by 36 is negative 1, b to the power of 6 divided by b to the power of 6 is also 1, so I end up getting a negative 1. So I've got a minus 1, and I'm all done with my GCF. Now I want to know, is it a difference of perfect squares? So my first factor is not because it is a monomial. But my second factor could be because it is a binomial, it has subtraction, and I also have perfect squares. So yes, it is a difference of perfect squares. So let's go ahead and factor it as a difference of perfect squares. The square root of x to the power of 8 is x to the power of 4 because x to the power of 4 multiplied by x to the power of 4 gives me the 8 that I'm looking for. The square root of 1 is 1, so I'm going to have a 1 here and a 1 here, and I have to have a plus 1 and a minus 1 to get my outer and my inner to cancel out. Now, don't forget that we had a GCF, so we have to bring that down. So we've got 36b to the power of 6 right here. Now I'm going to ask myself, for each one of my factors, is it a factorable trinomial? So my first factor is a monomial, so no, it is not. My second factor is a binomial, so it's not a factorable trinomial. And my third factor is also a binomial, so no, there are no factorable trinomials. My next question is, can I factor it by grouping? Well, looking at my first factor, there's nothing to group because it's a monomial. Looking at my second factor, there's nothing to group because it is a binomial. And my third factor, same thing, there's nothing to group because it is a binomial as well. So my last question is it completely factored? Well, I'm going to go through my list again and see if each one of my factors is completely factored. So this 36b to the power of 6, is there a GCF? There is no GCF. Is it a difference of perfect squares? It is not a difference of perfect squares because it is a monomial. It's not a factorable trinomial for the same reason, and we already said we can't factor it by grouping. So now let's look at x to the power of 4 plus 1. There's no GCF, there's nothing in common. It's not a difference of perfect squares because there's addition. It's not a factorable trinomial because it's a binomial, and we already established that we can't factor it by grouping as well. So looking at our last factor that we have here, is there a GCF? Nope, there's no GCF, there's nothing in common. Is it a difference of perfect squares though? Yes, it is because it's a binomial, there is subtraction, and we have perfect squares. So we will go ahead and factor this as a difference of perfect squares. Well, the square root of x to the power of 4 is x squared, and the square root of 1 is 1. And we can do a plus sign and a minus sign to get the outer and the inner to cancel out. But don't forget, we have to bring down our GCF, this 36b to the power of 6. And then this time we also have to bring down our x to the power of 4 plus 1. Because again, we're not changing our expression, we're just writing it in a different way. So now, I'm not going to go through this whole list again quite yet, because if you take a look at what we have here, this x squared minus 1, it's another difference of perfect squares because it's a binomial, there is subtraction, and we have perfect squares. So when I factor this x squared minus 1, the square root of x squared is x. The square root of 1 is 1. And again, we're going to have a plus and a minus. And now I will copy down my GCF, my 36b to the power of 6, my factor here, this x to the power of 4 plus 1, as well as our x to the power of 2, or x squared plus 1. And then we've got x plus 1 times x minus 1. Now let's go through our list again and ask ourselves, is it completely factored? Well, we've already checked our first factor and our second factor. So now we're going to check and see what's going on with each of our 3 new factors that we have since we've gone through our list. So looking at each one of my factors, there's no GCF. We no longer have differences of perfect squares because 2 of my factors have plus signs and my last factor has a minus sign, but this x is not a perfect square. I can't take it any further. Is it a factorable trinomial? None of these factors is a trinomial. They're all binomials. Can I factor by grouping? I cannot, because there's nothing to group when you only have 2 terms in each factor. So now I can officially say, yes, this is completely factored, and therefore 36b to the power of 6 multiplied by x to the power of 4 plus 1 multiplied by x to the power of 2 plus 1 multiplied by x plus 1 multiplied by x minus 1 is my final answer. All right, in our next example, we've got 12x to the power of 4 z squared minus 87x squared z squared plus 75z squared. Our first question is there a GCF? So if I take a look at each one of my terms here, they're all divisible by 3. So we can say for sure that there is a GCF. Not only are they all divisible by 3, and that's the largest number they're all divisible by, they all have z's in common. So I'm going to factor out, I've got z to the power of 2, another z to the power of 2, and another z to the power of 2. So I can factor out z squared. When I factor it out, 12 divided by 3 gives me 4. I can copy down x to the power of 4 because there are no x's in my GCF, and then the z squareds cancel. Minus 87 divided by 3 gives me 29. And then I've got x to the power of 2, and then the z squareds also cancel. Lastly, I've got positive 75 divided by 3, which is positive 25, and then the z squareds cancel each other out. So we're done with the GCF part. Our next question, is there a difference of perfect squares? So looking at my first factor, it is a single monomial, so it's not a binomial, therefore not a difference of perfect squares. Looking at my second factor here, it is a trinomial, so it is also not a difference of perfect squares. So now I want to see, is it a factorable trinomial? Well, if you see again, our first monomial here, our first factor is a monomial. It's not a factorable trinomial, but our second factor here is a trinomial. So I'm going to see if I can factor it as a trinomial. So I will set up my 2 sets of brackets. And if you look here, we've got 4x to the power of 4. These 2 first terms will multiply together to give me this 4x to the power of 4. For 4, I can either use 1 and 4 or I can use 2 and 2. I'll try 1 and 4. So I'll put 4 here and 1 here, and I'll use x squared because this second term that we have here is going to tell us that the outer and the inner are going to combine together to give us that x squared. Now I don't need the 1 here, so I'm just going to keep it as just x squared. We also know that our last terms will multiply together to give us this 25 right here. So I'll make a list of factors of 25. I can do 1 and 25, or I can do 5 and 5. So I'll try to place the 1 here and the 25 here, and I'll see what my outer and my inner will give me. My outer is 4x squared times 25, which is 100x squared. My inner is 1 times x squared, which is x squared. I'm trying to get this negative 29x squared, so I know that that's not going to work. So let's go ahead and try to swap the 1 and the 25. So my outer here will give me 4x squared. My inner here will give me 25x squared. And if they're both negatives, then they'll combine together to give us this 29x squared that we're looking for. So this is great. So this negative 4x squared here is going to tell us that this 1 here is negative. And this negative 25x squared here is going to tell us that this 25 here is negative. So now we know that we can factor this trinomial. Don't forget to bring down your GCF. Next, I'm going to ask myself, can I factor by grouping? So looking at my factors, I have 3z squared. I've got 4x squared minus 25, and then I've got x squared minus 1. In order for us to be able to factor by grouping, I need at least 4 terms, and none of these factors has 4 terms, so I can't factor by grouping. Our last question is it completely factored? And this is where we need to be extra careful. So let's take a look at each one of our factors and see our list that we have here and see if it's possible. So let's take a look at our 3z squared first. Is there GCF? There is no GCF. It's not a difference of perfect squares because I need 2 terms and this only has 1. It's not a factorable trinomial, and we've already established that I can't factor by grouping. So let's take a look at our second factor, 4x squared minus 25. Is there a GCF? No, there's nothing in common. Is it a difference of perfect squares? It is a difference of perfect squares because I have 2 terms. I have a subtraction sign, and both of my terms are perfect squares. Let's also take a look at this x squared minus 1 while we're at it. There is no GCF, but it's also a difference of perfect squares because x squared and 1 are our 2 terms. We have a minus sign, and you can square root both terms. Now we have factoring for a difference of perfect squares. So our first binomial is 4x squared minus 25. And the square root of 4x squared is 2x. And the square root of 25 is 5. And we can put a plus sign and a minus sign. So that's this first factor that we have here. Now our second factor, this x squared minus 1, I will set up my binomials for this as well. The square root of x squared is x. And the square root of 1 is 1, and then I'll have a plus sign and a minus sign. Again, don't forget to bring down your GCF. Now, looking at this right here, we have 5 separate terms. We have our GCF, we've got this binomial, another binomial, and a last binomial. We're going to go through our list of questions for all 5 factors all together at once to see if I can factor this any further. If not, it is completely factored. So, is there a GCF? Looking at each one of my factors here, there's nothing in common in any one of my binomials here or in my single GCF here. The next question, is it a difference of perfect squares? Well, I'm going to look for binomials that have subtraction signs. So we have this 2x minus 5 here, but none of them are perfect squares, so that's not a difference of perfect squares. We have this x minus 1, we have a subtraction sign, but the x is not a perfect square, so we don't have a difference of perfect squares. Now I'm going to see, is it a factorable trinomial? Well, I have no trinomials as factors here, so there are no more factorable trinomials. And then to factor by grouping, I need at least 4 terms in each factor, which I don't have either. Meaning the answer to this question is yes, it is completely factored. Making 3z to the power of 2 multiplied by 2x plus 5 multiplied by 2x minus 5 multiplied by x plus 1 multiplied by x minus 1, our final answer. So this is the end of part 1. Make sure to check out part 2 for some more challenging factoring completely questions. Thank you for watching. If you have any questions, let me know in the comments below or at lulumath.com, where you can also find blank or completed notes for this video. If you found this useful, please subscribe and share with others. Thank you, and we'll catch you next time. Bye.